I see a red light now. Okay, we talked about arcs having strong plasma jets that were produced electromagnetically. Essentially, whenever you have a current going through something, it will have a what they call pinch force. There's a self-magnetic field around it. The current's flowing axially, and that means that the force will be directed radially inward. So a current conductor will try to squeeze itself down and pinch itself. And the electromagnetic forces in the plasma influence drop transfer because of this strong plasma jet. They influence arc stiffness. Stronger the jet, the harder it is for sideway breezes to blow it away. They influence out of position welding. Small drops actually will be carried upward or shot sideways against gravity by this strong jet. It also will influence pool surface depression. And up to about 250 amps, you don't have much surface depression. Between 250 and 450, you start actually seeing the number of defects form. And there's a lot of welding that doesn't occur between 250 and 450. There is welding that occurs in that range, but you've got to get your parameters set right so you don't get these instabilities in the pool that are caused by the deeper pool surface depression. And then at very, very high currents, and I would say very, very high, I mean above 500 amps, you actually start getting, you're just gouging and blowing away stuff. And now you have to get into flux shielded processes like submerged arc, and we discussed that briefly. I didn't say a lot about pulse current, but I did mention that we have pulse current power supplies. They've actually had them since the 1960s, but in the 1960s they were really old. They were playing games with what's called a transformer rectifier power supply, where you just have diode rectifiers and a transformer, and they would basically get pulsing at either 60 hertz or 120 hertz, and they didn't have a whole lot more to play with. Nowadays, in the last 15 or 20 years, with inverter power supplies, the size of a welding power supply is considerably smaller. They can weigh a few hundred pounds as opposed to 1,000 pounds or more, because they got a lot less copper in them with these solid-state inverters, which we won't go into in any detail. But now you can pulse for several milliseconds at several hundred amps, because these power supplies actually operate at anywhere from 20 to 40 kilohertz before they do the rectification to DC. And that allows all kinds of ability to do all kinds of fancy things with the arc. And in fact, if you want, with some of these high frequency power supplies, you can actually use the arc as a loudspeaker. And in fact, there is a German firm sells for about $2,000 or $3,000 a little gas tungsten arc loudspeaker system. And they claim that it has much better, since you're dealing with the plasma, you don't have the mechanical inertia of a regular speaker. And they claim it gives you much better fidelity. It may, I'm not sure it gives you that great a fidelity from some of the types of things that we've done, but you know, it's sort of like you can sell anything to a golfer. Well, there's certain audio files that you can sell things to, and so they actually have done it. We have a power supply downstairs that Don Galler designed about 15, 16 years ago, actually designed it about 20 years ago, which is nothing more than a 20 kilowatt transistor bank, and it will pulse to 5 kilohertz without any roll-off and without any significant roll-off in the amount of current you can pulse. So you can pulse 600 amps at 5 kilohertz. At 20 kilohertz, you're not going to be able to pulse 600 amps. You're going to start losing some of your fidelity. But actually, we have set it up and actually modulated it with a microphone, and you can speak over the arc. Okay. Actually, Professor Lieb in electrical engineering has gotten a patent on using fluorescent lights, which are nothing more than arcs, and modulating those so that you can basically have a communication systems through your lighting system in your building, so far as that goes. So pulse current arcs, in this case, they influence droplet transfer. If you pulse for a couple of hundred amps, that same pinch force, that same Lorentz force, will actually, the current's going through the little drop on the tip of the melting electrode, and it will squeeze that off. It's sort of like milking a cow, if you will. You just, every now and then, you squeeze and the drop shoots off. If you coordinate it in around the 100 hertz type of frequency that these drops are coming off, if you drive it at a 90 hertz or drive it at 140 hertz, you can actually get the drops to come off. If you try to drive it too far away from its natural frequency, then it won't respond. And it also increases the arc stiffness. Okay, so that's enough on plasma jets. I want to talk, anybody have any questions? If not, I want to talk briefly about arc ignition. Well, partly because this is another place where there are errors in the welding handbook, and that's always fun to talk about. But also to kind of point out, it's not as easy to start an arc as a lot of people think. First thing that you will find in the old welding handbook, people will talk about Paschen breakdown. Well, Paschen was an engineer or a scientist back in the 19th century who basically, after Humphrey Davy discovered arcs, found that if you brought two electrodes very, very close together and you had several thousand volts, that the air in between would break down and you would start an arc. You didn't actually have to touch the electrodes like Humphrey Davy did. You actually could start the arc without actually touching them. He'd get them within like 1/10 of a millimeter, a little more than a human hair apart, with like 1,000 volts or 2,000 volts, and he could get a discharge start without actually getting physical contact. And that was called Paschen breakdown. Now it turns out the next thing is called field emission. And in field emission, which became popular in the first part of the 20th century, mostly because people were studying vacuum tubes and cathode rays. And they wanted to know, how did you get the electrons out of the cathode? If you go to an arc physics book today, there are about 30 different theories on how the electrons go from this low potential well of the Fermi level bound in the metal out to the free space energy of an electron out here in the gas or the vacuum. I mean, there's a lot of energy that has to go into that, and obviously there's a tunneling phenomena that goes through. Quantum mechanical tunneling is part of it, but even today there's not a generally single accepted theory for exactly how you get cathode emission. But one theory that does work and has been worked out quite in great detail back in the early days of quantum mechanics was field emission. And it turns out field emission, if I have thousands of volts, or actually let me state it another way, if I have 10 to the 8th volts per centimeter, that's a lot of volts, okay? I can actually have enough of an electric field that I get tunneling through the barrier. There's a potential barrier as you go from the Fermi level up to this barrier up here, but if I put a steep electric field on that, out here in the vacuum, I'm basically lowering that potential. And I actually have an overhead of that, but that's okay. I've loaned it out for a second. And basically, instead of having a potential at this energy level and this energy level, by putting a very steep electric field on this, I essentially drop that down, and the electric field is pointing in gradient in that direction. I've lowered the barrier, and I get tunneling through that barrier. So field emission actually has worked out very well, and it occurs, but it takes thousands of volts. Well, I don't have thousands of volts in a welding power supply. If I did, I'd be electrocuting people. So field emission doesn't work for welding, even though the welding handbook says it does. They just forgot they don't have enough voltage to do it. So the Paschen breakdown turns out to be nothing more than a subset of field emission, because if I start getting 1,000 volts across a 1/10 of a millimeter, that is 10 to the minus 4 meters, let's say 10 to the minus 2 centimeters times 10 to the third, that's 10 to the 5th. That's not 10 to the 8th volts per cent. Wait a second, I think that's supposed to be 10 to the 8th volts per meter. I probably wrote that down wrong. 10 to the 8th volts per meter. That's up to 10 to the 5th. That's not quite the 10 to the 6th volts per centimeter I need, or 10 to the 8th volts per meter. I can get that, so let me back up. If I've got Paschen breakdown at 1/10 of a millimeter, that's 1/10,000th of a meter. And if I got 1,000 volts, that's 10 to the 4th times 10 to the 3rd, 1,000 volts, right? That's 10 to the 7th, and that's only 1 order of magnitude away from the field emission at 10 to the 8th volts per meter. That means that I'm almost there. It turns out if I have two solids, if I have a surface and I have some little protrusion there, there will be a stronger electric field around the tip than there is on the flat surface. And so basically Paschen breakdown is really just field emission. They didn't know about field emission when Paschen was doing his studies. And people originally thought they were two different phenomena because they didn't understand how small little surface irregularities can enhance the electric field. If I have an electric field and I draw the potential lines across here, they bunch up at the tip. If this is a metal surface down here, they're going to bunch up here and give me a steeper gradient at the tip. It's just like a stress concentration if you're familiar with mechanics. Stress concentration in a notch. An electric field concentration at a point on the conductive surface. So it turns out Paschen breakdown and field emission are the same. To give you an example of one of the ways that I ran into this, I used to be on the board of directors of a company called Nashua Corporation up here in Nashua, New Hampshire, and they made, among other things, they used to make refill laser cartridges. They were the largest refiller or remanufacturer of laser cartridges. And to remanufacture the laser cartridges, they had to make the photosensitive drum that takes the electric charge. You know, you shine the light on the drum and you charge up the surface, and then the toner comes across the surface and it gets attached electrostatically to this drum, and that's how you store the image. And then you roll the paper over that, and these little black plastic particles on this heated drum that are only located where the light hit or didn't hit, get fused to the paper. You know how a Xerox machine works, basically? Okay, well, okay, the Xerox machine, the Xerox process is, if I have a surface and I shine light on it, I can develop some charges. And depending on, originally Chester Carlson, who invented Xerox, but then he sold his patent rights cheap to a company called Xerox. He basically took selenium, which is a semiconductor, and when you shine light on the semiconductor, you can store a charge on the surface. You can build up a charge and store a charge. And then you basically coat this thing with electrostatic particles. This will be a negative particle. That's your toner in your cartridge. Okay. You can either have positive, you can have the positives and negatives go either way. Some toners are positive toners, some are negative toners, depending on what type of conductive surface or semiconductive surface you have. So you shine light on this. In some areas where the light hits, you build up a charge. In other places it doesn't. You then put the toner on there, and now the toner is just sitting on this electrostatic surface. Now the electrostatic surface in the real world is a drum, okay, just a cylinder. And now if you bring a piece of paper over that, you can melt this little plastic particle, the toner particle, to the piece of paper. That's why the paper comes out warm out of a laser printer or a Xerox machine, because you just melted the plastic onto the surface. Does that all make sense? So now you know how xerography works. Okay, turns out, so they had these little, they didn't have selenium, they actually had aluminum cylinders that they had diamond turned to a very smooth finish, and then they coated them with a little polymer. They had their own proprietary polymer that they had developed that would absorb the charge when the light hit it. And then, of course, you'd have the toner particles come in and stuff. Well, the problem was they'd never had any real problem for a long time doing this, and all of a sudden, every piece of paper that came out would have a few little black specks. Now, you and I probably wouldn't even notice them, but if you're doing quality control, they would have the same spot every time off that drum would have a particle, or have a toner particle. And so they asked me to come up and look at this, and it turns out this coating was only about something like 0.2 millimeters thick. It's like 8 thousandths thick. So a couple of sheets of paper. And they had 600 volts across this thing in order to develop the charge. and they had already done some work, and they had found that the spots, they went to drums, and they would section it, and they would dig down and clean off the polymer, and they found every spot on the aluminum surface. If you looked in the microscope, you found these little jagged inclusions right there on the surface. Basically, these were inclusions, aluminum oxide inclusions in the aluminum metal that they were making the drum out of. And I said, well, I basically said, well, what's the field gradient across here? And if I've got 600 volts across 0.2 millimeters, and that works out to 0.2 or 2 times 10 to the minus 4, and this is 6 times 10 squared, and that's 3 times 10 to the 6th, if I did that right, volts per meter. And these were very, very sharp particles. And basically they were getting field emission that was putting a charge on there whenever, as they applied the voltage. And it was because of these sharp particles on the surface. Now the solution to this, one of the solutions, was to just put a little nickel plate layer and bury those sharp particles. They were getting the sharp particles because they were doing single point diamond turning. If you'd gone through and done regular turning with a regular tool bit, you would have smeared enough of the surface that you would have smeared the soft aluminum over the particles. But they wanted the fine finish of single point diamond turning, and single point diamond turning was sharp enough, it was uncovering these inclusions and not smearing aluminum over the surface. So we could electroplate the surface with nickel and bury those things, and the problem went away. The problem was these little things were worth, you don't pay that much for a laser cartridge, and that was an extra 50 cents for each drum, which basically killed the profitability. So it was, I'm not sure how they ever finally resolved it, but at least we figured out what the physics was. Okay, and it was field emission. Well, field emission doesn't occur in arc welding, even in spite of the welding journal, or not the welding journal, but the welding handbook. What does work is separation of the electrodes initially in contact, same way Humphrey David did it originally. Brought two electrodes together, pulled them apart, and an arc struck. What you do with the welding electrode, if this is my welding electrode, the welder looks at it, he's got, his helmet has got kind of a hinge up here, and so you can lift it up, and it's held by friction. If he just kind of snaps his neck a little bit, the inertia causes the helmet to drop down, so it goes like that. Now he's got the shielding, and he goes in there, he just kind of comes in and just touches the surface, and all of a sudden you get a big spark, right? If you've got the right kind of power supply behind you. Well, how does that occur? It turns out Ragnar Home and some other people, and Ragnar Home was one of these German scientists that the United States brought over after World War II, Werner von Braun, he was a rocket scientist. But Ragnar Home was an electrical contacts expert. Actually, his wife was too, but this book is goes from, well, let's see, he was born in 1879, but this book is 1967. Electrical Contacts, 4th edition, Ragnar Home, PhD, in collaboration with Elsie Home, PhD. So she doesn't even get top billing. She was his wife, anyway. But back then, I guess German scientists, even if their wife did the work, they didn't give them credit. She's got small print here. Anyway, Ragnar Home was an electrical contacts expert. He went to work for Westinghouse, and he wrote this book, which by 1967 was in its 4th edition. Still, the electrical contact conference that's held every year by the IEEEs, the electrical engineers, is called the Home Conference, even though Ragnar's been passed away for years and years. If you go through here, he actually worked out the math of 2 asperity contacts. So these are the little microscopic contacts that come in touch with each other when you touch 2 solids together. And if you look at the voltage across here, you can say there's a V0 over 2. There's a voltage V0 across here if you have a potential on here, and a minus V0 over 2 over here. And it turns out you solve Laplace's equation and you get around that contact point, you can see what the electrical field lines would be around there. by solving Laplace's equation. Now it turns out if you have current going through there, depending on the resistance of this contact, you will generate heat at that interface, and the heat will flow away, and it turns out the heat flow also is solved by Laplace's equation. So in terms of the field, your voltage field has exactly the same field lines or potentials as your temperature isotherms. So you've got a voltage of V0 over 2 coming from this surface out, and that's what these lines are supposed to represent, is the voltage potential. But it turns out the temperature field has exactly the same shape, the temperature isotherms. And so if you want, you can go to Ragnar's book and he'll solve the problem for you. But basically there's an equivalency between the voltage and the temperature, such that if the voltage is in volts, the voltage squared divided by 8 is 1, this is the constant of proportionality, 1.2 times 10 to the minus 8 of T theta at the interface, where it's heating, minus T0 squared. And this constant includes things that have to do with the electrical resistivity and the thermal conductivity, as you might imagine, that you're solving for voltage fields, or you're basically solving V is equal to IR, so you have the electrical resistivity in there, and you're solving Fourier's first law of heat conduction, which has thermal conductivity in there, and that's all contained in this constant. It turns out, if you want to know, they then define from that equation, using that constant, different types of voltages, which they call the melting voltage or the boiling voltage for metals. Now we know that copper melts at 83 degrees centigrade, which is almost 2,000 degrees Fahrenheit. It turns out if you put all that in for copper, you find the equivalent voltage for that temperature in copper is 0.41 volts. It doesn't take 1,000 volts to melt copper at one of those little asperity contacts. It only takes 0.4 of a volt. And in fact, in the back of Ragnar's book, he has an appendix which, for a bunch of different metals, he gives you the melting voltage and the boiling voltage. It turns out, if you want to look at that, it turns out the highest voltage, I think on there, is the boiling voltage of tungsten, which is only 1.1 volts. You can vaporize tungsten at an asperity contact with 1.1 volts. So if I bring these two things together and I pull them apart, the resistance has to go from some low value to an infinite value, and as it does that, the resistance has to pass through some voltage or some value that will essentially vaporize whatever the material is. Not only will it vaporize it, it'll heat it up, give it enough superheat, you'll ionize it, and as soon as you have some ionized gas and voltage across there, you strike an arc. So this is basically touch starting to initiate an arc. The other way, so what we have here is these two don't initiate welding arcs, these two do. The last one is high frequency. In high frequency, you ever seen a Tesla coil? If you take a Tesla coil and you put it up against the fluorescent light, you don't even have to have the fluorescent light attached to a power source. The very high frequency, RF frequency of the Tesla coil will actually light the fluorescent light, because the very high, rapidly oscillating magnetic field will essentially resonate the electrons off the atoms, if you will, and you'll ionize the plasma. So you can take a Tesla coil and just a fluorescent light hanging here, you put the Tesla coil up next to it, and just the magnetic field interaction will create ionization within the fluorescent light. Well, you can start an arc that way. And in fact, on some welding power supplies, particularly when we're welding aluminum, which has this refractory oxide, I mentioned yesterday how we often gas tungsten arc weld aluminum with a voltage, with a AC current, or AC power, because we want to take care of cleaning off this refractory oxide. You often will lose the arc in aluminum because the oxide becomes refractory and you can't sustain the arc. So they actually have a high frequency overlay on a gas tungsten arc welding power supply. You flick a switch and they actually generate a lot of RF noise. So if you go down to my lab and you have the radio on and someone wants to weld aluminum and they got the high frequency overlay on, then the radio goes berserk and all you get is a bunch of static because you're generating all this RF noise. But that high frequency helps stabilize the arc and helps it reinitiate. But in general, the arc is initiated by contact, electrical contact, or separation of contacts. So why do we spend all that time? Yep.
I think we ought to get a radio for the lab so we can test that out.
Well, we had a radio for the lab. Just 20 years ago, we had a radio that was, at that time, it was no more than 20 years old. So you sure our 40-year-old radio is still not there? It used to be up on the wall. No, I think the radio Chris is talking about is probably a very fancy radio. He likes electronics. Anyway, well, why did I bring all that up? It turns out when you're arc welding with robots, it's not very easy to initiate an arc. I mean, if the advantage of a human can, I mean, I can go up towards that surface of that table and I can stop short. Or I could go up fairly quickly and I can change to a different scale of sensing and control and touch it very gently, right? Robots tend not to be able to do that very well. They have to sense what's there. Of course, I was doing it with my eyes, and I guess a robot might be able to do it with their eyes. Robots tend to have less intelligence than the average person. You may or may not believe that, but NIST did a study and showed that the average IQ of a robot was 10. Okay, and it's interesting to me when I go out in industry and find these managers who want to replace their workforce with robots because they're going to get better quality. That says something either about the manager's IQ or the employee's IQ. I'm not sure which, but anyway, they're going to improve the quality of their workforce by replacing it with something that has an IQ of 10. Okay. What it really says is the managers don't know how to make use of the intelligence of their workforce, but that's another lecture, I guess. Nonetheless, if I want to start feeding a wire that I've been arc welding with into and do a touch start, typically, if it's liable to just kind of run into the surface and jam into the surface. The surface of that tip of that wire is typically oxidized from, it's red hot and it cooled down in the air, and if I run it into the surface, it doesn't actually make electrical contact because I got an insulating oxide layer on the surface. So I've seen robots, welding robots, where after it makes an arc, the robot takes it over to another place, runs the wire down, and some little cutters come in and cut a nice new tip without any oxide on it, just a little diagonal cutter. So I have a chisel tip. And now when I come in, the robot will come in, feed the wire in, and I have this little chisel tip, and as soon as the chisel tip hits, you'll get a current flow through there, and if you have enough current, you'll basically blast that thing apart, and you'll start an arc that way. However, with the new inverter power supplies that we were talking about earlier, what they do more commonly is when they shut off the arc, they make sure that the gas supply that protects the thing from oxidation runs a little bit longer, like 5 or 10 seconds, to allow the tip to cool off once you stop the wire from the previous weld on the robot. And then, in addition, the current, you may have been running along welding with some current on the previous weld. This is time, and right as you shut it off, instead of just going down like that, you put a big peak in like that, and you squeeze the drop off the tip. You go up to 300-400 amps for 10 milliseconds. Just squeeze that drop off the tip so that you get a nice sharp tip with just a little bit of metal there. So now when you come back in to restart it, you can start it. So there are actually more tricks out there than you might think. Any questions? Okay, so we finished up arcs. Now we actually have to go to the most important part of the course, in terms that this actually part of the course will allow you to solve most of the, or three of the problems, more of the problems than any other thing. Some of you have already done this. And this is heat flow in welding. And we'll finish it up on Monday, but basically, and this is not just heat flow in welding, this is kind of a heat flow lecture in general. I ended up, for my doctorate, I ended up minoring in heat and fluid flow. So I took these courses in the math department and over mechanical engineering, and I didn't have the foggiest idea what they were talking about. I mean, all these solving of differential equations and different coordinate systems and transformations, and I'm sure it's all very exciting to them. But I didn't really come out of those courses with a very good feel for heat transfer in general. But in fact, now I would say that about once a week, either working with my students or consulting or somewhere, I end up solving the heat flow equation in my head with a technique that they actually sort of taught, but they never emphasized. And so it's sort of one of the tricks that they use in universities is a lot of professors like to show you how complex things are, and they don't really want to show you how simple things are. Or they don't want to teach you the shortcuts on how to do things, because that way they wouldn't have their advantage of knowledge over you, right? Or whatever it is. I don't know exactly why they did it, but there's something called the Fourier number, which is a dimensionless number. We've talked about dimensionless numbers before. The Fourier number, the symbol is FO. And the Fourier number is just the distance x in centimeters divided by the square root of the thermal diffusivity of the material, which is in centimeters squared per second, times time, which is in seconds. So I got centimeters squared per second times seconds, which gives me square root of centimeters squared, which is centimeters, right? Divided into centimeters, and that's dimensionless. So the Fourier number is a dimensionless number, and it turns out the Fourier number, if you were to write down Fourier's second law of heat conduction, which is the change in temperature with time in an object, is equal to the thermal conductivity divided by the density times the heat capacity, is equal to the gradient squared of the temperature with distance, okay? Now, if you want, you could put grad squared T in there, and so you can put it in 3 dimensions, right? I've just written it down for a one-dimensional heat flow. Turns out K over rho C sub P is not a fundamental property. It's a derived quantity because it comes from these 3 more fundamental properties of thermal conductivity, density of the material, and heat capacity of the material. But alpha, which is the thermal diffusivity of the material, comes out of Fourier's second law. And it tells you how fast something is going to heat up and tells you what in proportion to the temperature gradient that's in the material. So, and I'll go through that stuff in a second. I have found it's very useful to memorize a few constants of alpha for certain materials. Turns out alpha in centimeters squared per second for copper is 1. That's an easy one for me to remember. For steel, it turns out to be a 1/10. For aluminum, which is somewhere in between, it's 0.6. For stainless steel, it's 1/20th of a centimeter squared per second. And titanium, it's about a 20th. It turns out if I put some ceramics down here, they might be down at 0.01. A very porous insulator might be 0.001, thermal insulator. So it turns out the highest thermal conductivity material, thermal diffusivity material is not copper. Silver is about 1.2, by the way. Pardon me? Gold. Gold is like 1.3 or 1.35, something like that. So gold, in fact, MIT had a patent one time, someone, a mechanical engineer, patented a way to detect whether a gold bar was pure by essentially measuring heat transfer through it. You heat it up on one side and you measure at what time it took to reach the temperature on the other end of the bar. And since you can't counterfeit the thermal diffusivity of the material, and if you alloy it with other junk, this was supposedly a way to measure the purity of gold bars. If you were, in some Swiss bank and you want to make sure someone hadn't slipped you a false bar. I don't know that it ever made any money, but in fact I doubt it did. But nonetheless, gold has the highest thermal diffusivity of any metal at room, or any material at room temperature. Turns out diamond below room temperature has even higher thermal diffusivity, and that's one of the reasons people would like to develop diamond substrates for semiconductors, because you can get the heat out better. I think it goes up to like 2 or 2.5 or something in diamond at minus 100 degrees. Of course, that means you have to run your semiconductor at minus 100 degrees, but diamond has very good thermal diffusivity. And really, thermal diffusivity only varies over about 3 orders of magnitude, unless you get to air, which is like 10 to the minus 4. But air is an insulator, right? I mean, of all the things we have in the world, unless you want to start going to a vacuum, but at 1 atmosphere pressure, there's only about 3 or 4 orders of magnitude variation in everything in terms of thermal diffusivity of materials. So how do you use this? Well, one way to use it, to give you an example, if I wanted to know the heat affected zone of a weld in a steel arc weld, I know that my Fourier number basically gives me an equation if I wanted the Fourier number to be 1, okay, and the Fourier number is a ratio of the distance that the heat travels proportional to the time. And I guess I didn't tell you where it comes from. Turns out this equation I had before, this is basically called the diffusion equation in mathematics. And I had to take a course over in the math department that taught me how to solve the diffusion equation in all its varied forms. But this is basically the diffusion equation. Something with respect to time is proportional to the curvature. The square of a gradient is a curvature. Okay? So whether we're talking heat diffusion or mass diffusion, in mass diffusion this is called Fick's second law for Fickian diffusion. If you're talking about, you could actually write this down. We don't usually write it down, but Ohm's law, it would be a steady state electrical diffusion. We don't usually have non-steady state electrical diffusion because when we have that, we're getting things up at the speed of light. But anyway, so there's various. You can also have diffusion of viscosity in fluids, but we won't get into all that. But the basic diffusion equation will always come up, if you're doing thermal diffusion, will always end up with the Fourier number as a dimensionless number. You can rewrite that differential equation in a way that you always have some function of the Fourier number. Whether that function is an exponential of x over square root of alpha t, whether it's an error function, whether it's a Bessel function, but you always have that dimensionless number. You can't take the exponential if something has units. You have to take the exponential if something is dimensionless. And whatever the solution to the diffusion equation is, for whatever geometry you have, you will end up with the Fourier number. So if I want to know how heat travels in a material, transient heat flow, I mean steady state heat flow, you can do Fourier's first law, that's just linear gradients and stuff. That's not in a rectangular system. That's not too hard. But transient heat flow, that's hard. They usually tell you got to go solve the partial differential equation, right? Well, you don't have to. You can do it you can solve the transient heat flow problem in your head if you just want an order of magnitude answer. The width of the heat affected zone in x, with x, is going to be proportional to the square root of the thermal diffusivity of the material. I'm doing steel here, but you could do copper or aluminum by putting in a different thermal diffusivity. Well, what's the relevant time for the creation of a heat affected zone in the material? Well, remember we talked about the weld pool traveling along, and if this is my weld pool solidifying, and this is the length L of the weld pool traveling at some velocity v, this is the molten metal, and the heat's flowing out to create a heat affected zone adjacent to it, and it starts flowing out right here when the pool first hits it, first hits it, and then when it passes back here, that's the length of the pool. And so the time, the interaction time of that molten zone with the material next to it is just L over V, right? So that's the interaction time. If I put the interaction time in this under the square root, typical travel speed for an arc weld, gas metal arc weld, might be 12 inches a minute. Well, that's a half a centimeter a second. I divide that into the length of the pool, might be about a centimeter long. So that's a half times 0.1, which is 0.05, and the square root of that is about 0.16 or so. Anyway, whatever it is. I don't know, it's 0.2 something. Anyway, this all works out to about 4 millimeters. And 4 millimeters is a little over 1/8 of an inch. If you look at one of these, that HY80 weld I've passed around a few times, it has a heat affected zone that's about 1/8 of an inch in size. So within about 20 or 30%, I can calculate the width of the heat affected zone, and I can do that in my head. Yep.
So if I go faster, does that mean I have a smaller heat affected zone?
You have a smaller heat affected zone up to some limit that we talked about before. If you go too fast, then basically it's not just the Well, actually, if you go very, very fast, this pool gets to be very, very long, and you run into some other things. Okay, it takes time for the solidification to slow down, but you'll get a smaller heat effective zone if you go faster, but only within because of the square root dependence, you can only get it down by about a factor of 2. Now, to give you an example, when I mentioned this hot isostatic press that blew up that had 10-inch thick steel walls. Some of the steel walls were 17 inches thick. And I remember when I was out there 2 days after the thing, and we were trying to understand what happened and why this thing blew up. The thing had been running for about 3 hours when it blew up. They'd started heating up the steel, or heating up the vessel, which caused the steel walls to start to heat up. And I remember, well, we know it was steel, and I just took 12 inches because some parts were 10 inches and some parts were 17 inches. I wanted to get a ballpark of how long it takes to heat up steel, that thickness of steel, because I didn't know for sure. Well, that's 30 centimeters. 30 centimeters squared is 900. I actually square the Fourier number, so x squared is equal to alpha t. 900 divided by 1/10 is 9,000 seconds. That's about 2.5 hours. Well, I knew at that point that essentially what had happened was, well, in fact, I left there saying the thermal stresses were important, because if I have the Fourier number and if the Fourier number is equal to 1, that means that in the time with Fourier number equal to 1, it means for some finite thickness material, X, it means if this is hot on one side, the heat will just start to be showing up on the other side when the Fourier number is equal to 1. Now, it turns out for the exact solution to this, I happen to know, because I took these courses, this is an error function solution for just a flat plate. And I know that when the Fourier number is 1, that this has actually raised its temperature by 10% of the maximum temperature on this surface. But I mean, if I've got 100 degrees on one side, then on the other side, when I get to a Fourier number of 1, that means the material is raised 10 degrees in temperature. I wouldn't be able to feel that probably with my hand. But if I got 1,000 degrees over here and it's raised 10 degrees in temperature, I'd be able to start to feel the heat by the time I get to a Fourier number of 1 for that thickness steel. So with a Fourier number of 1, the heat has just started to penetrate. With a Fourier number of 10, the material is much thicker, and it's as if it's infinitely thick. With a Fourier number of 1/10, the heat penetrated all the way through, and this other side is rising in temperature to equilibrate. So thin samples with small Fourier numbers will essentially heat relatively uniformly. But what's a thin sample? It's all relative to the time of heating. You know, if I were to, if you stick a roast in the oven and you just pull it out a minute later, it didn't heat up. It's got too much thermal mass. It takes a certain amount of time. You stick it in the oven for 3 days and it's going to come back and be completely burned. If you figure out the Fourier number for that roast, and there is a thermal diffusivity of heat in beef, okay, you're going to find that you have a very, very small Fourier number if you're very, very long times, like days. If you stick it in for minutes, a couple of minutes, it's still very thick and it's going to be rare in the center. You want it somewhere it's going to be raw in the center. It can still be frozen in the center if you only stick it in a couple of minutes. If it was frozen in the center, if you want it to be rare in the center, you've got to cook to a Fourier number of around 1. Now, people who like it well done may cook to a Fourier number of 3. But people who want something really, really rare, they're probably cooking to a Fourier number of 1. Okay. So, you know, we should rewrite all the cookbooks and just tell people cook it to a Fourier number of. Anyway, so that's basically thick and thin, and you want to know whether something is thermally thick or thermally thin. And I think it's the last problem. If you do the homework set, I basically ask you about resistance spot welding, and I give you 2 different time scales. The time in which the current is flowing, which is like 1/5 of a second, or the time between welds, which is more like a second. And it turns out that factor of 5 changes the whole thing from being thermally thick so that the water cooling doesn't have an effect to being thermally thick. Actually, it's in here somewhere, and it does start to have an effect. Okay? So cooling of the electrode within 1 second in spot welding actually has an effect, but during the time of the weld, in a fifth of a second, you might as well not have the water there. It can't see the water that far away. So if you want to get some perspective on distance, material property, thermal diffusivity, and time, that's all you need to know. Now, it helps if you understand a little bit more about some of these things and have solved these things a few times. There's also the problem of convergent and divergent heat flow. If I have a circular geometry, well, they taught me when I was a graduate student that I had to solve the Bessel function equations. Okay? I had to go to a table of Bessel functions to solve the diffusion equation for heat transfer in a cylindrical geometry or spherical geometry. And it depended if I was convergent, I would get one set of Bessel functions because the area, as the heat's moving from the outside in, the area is getting smaller, and so the heat's starting to accumulate on a smaller surface. And that means if I was purely planar, this might be my temperature gradient, temperature versus distance, for a planar geometry. But if it's convergent, it's going to heat up faster, by maybe a factor of 2. But if it's divergent, if I'm heating from the inside of a cylinder, and that means the heat has to spread out and heat up a larger mass at a greater radius. It's divergent, that means it's going to heat up more slowly, by maybe a factor of 2. So convergent or divergent might change things by a factor of 2. If I want to know the heat flow for something within a factor of 2 or 3, I can just run the Fourier number. And the trick is, and what they don't tell you in school, is that 95% of all heat flow problems, you're either thick or you're thin. And a lot of times that's all you need to know. When I went out there to figure out why this pressure vessel blew up, I needed to know why it blew up after 3 hours of heating. If it was thick, that meant that the heat hadn't even gotten to the outside surface. If it was thin, it means the whole thing was uniform in temperature. When I ran the Fourier number, I found I was near a Fourier number of 1. That meant it was as non-uniform as it gets. Okay, I mean, think about it. Let me go back to my plots here. If I'm thin, if I had lots and lots of time and my roast beef is getting really well done, it's fairly uniform in temperature, and there's not a lot of thermal stress in here because the temperature gradient is not very big. If I go over here, yeah, it's a big temperature gradient, but this material is all cold and has a lot of strength. This material, the hot material, this might be going into compression, but look how much more material I've got out here to support all the compressive stress here. Okay, I have maybe 1/5 or 1/10 of my material is in compression, which has to be distributed over the other 80–90% of the material, which has to go into tension, which means the tensile stresses out here in the cold material are 1/10 or 1/5 the value of the compressive stresses here, because the stresses have to equilibrate. Everybody following what I'm saying there? If I'm like this, somewhere near a Fourier number of 1, I have absolutely the worst possible tensile stresses on the outside of this vessel. Now, one thing I had learned in this whole thing is I saw the fracture origin was on the outside. All the theory of this vessel was the fracture origin should have been on the inside. But I looked at it and it was on the outside. And so I ran the number in my head. You know, this is one way to impress people, just like talking about movies that win welding awards, okay? It impresses people. You know, I'll be sitting in a meeting somewhere, and someone will be talking about some heat flow problem, and I'll say, oh, no, well, such and such. And they said, how'd you do that? I said, I just calculated it. And they said, well, you didn't have a piece of paper and pencil? I said, no, I didn't. Because most of the time, you know, I can simplify these numbers, in most cases, to something 30 times 30. I can do that in my head, okay? Divide by 1/10. I can do that in my head, okay? 9,000. Well, that's 2.5 hours, right? It's not hard. And actually, I actually enjoy doing this. to be able to solve heat flow problems. And other people, well, they just kind of start stuttering and stuff because they don't really believe that it's correct. That you can get a transient heat flow analysis in 60 seconds in your head, but you can. And 95% of the time, you don't need to do the fancy differential, solve fancy differential equations. 95% of the time, you just need to know whether it's thick or thin, and then you can draw all kinds of engineering conclusions from that. When you find it's right there in the intermediate region, where near a Fourier number of 1, that's the one time out of 20 that you have to go and actually solve the whole problem. But that can be done. But you don't need to know, you don't have to go solve the problem to find out whether it needs to be solved. You can do simple dimensional analysis. And this doesn't just apply to heat flow, it applies to diffusion. If you know the diffusivity of something, and typically people worry about hydrogen cracking in steels. I haven't had a problem like that for almost a month, okay? And people said, well, they were claiming that you heat up the steel for 2 hours afterwards and you'll diffuse all the hydrogen out of a 7-inch thick weld. I said, I don't think so, because I happen to know the the mass diffusivity of hydrogen is like 10 to the minus 6 or 10 to the minus 8 centimeters squared per second. And you take 4 hours, and you do 10 to the minus 6 times 4 hours, which is about 10,000. And that means the square root of 100, the square root of 100 is 10 centimeters. It only goes 10 centimeters. 10 centimeters is 4 inches. You're not going to get stuff out of 7 inches of steel. Its thickness is much thicker than the distance that you can move hydrogen out of steel, even if you use the 10 to the minus 6. If you use the 10 to the minus 8, you're only going to get the hydrogen out of that top ½ inch, not the top 4 inches if you're doing 10 to the minus 6, but only a top ½ inch if you're using 10 to the minus 8. So I just did that one for you, okay? And so people will throw out numbers all the time without ever checking the numbers with the Fourier number. And if you do use the Fourier number, you will find that it works very, very efficiently for 90% of your problems. Okay, we'll talk about lasers and electron beams on Monday.